Hello, it is I, your internet friend, Robert Guderian. Today we're going to talk about different types of languages and how they interact with what we want to do and how that can change based on the language, which is really neat. Lots of us learned Java as our first programming language. That is a compiled language. Most of us learned in something like Dr. Java or maybe Genie, and you have to hit compile and then execute. If you didn't hit compile before execute, it'd throw a fit. Or maybe you use processing, which is kind of a compiled language, which is interesting. And some of us did learn Python first, which is handy, which is an interpreted language. And now, what does that mean to us? And why does that change things? Well, imagine we have a world where we have a Hello World program. This is inside of my building chapter. It has a make file. You can type make, and guess what? It'll build it with Clang. You can use GCC too if you wanted to. And that actually made a program. Here, I'm going to say make clean before I really start here. And we can see that there's only two files here, a make file and a C file. Hello World is pretty bog standard. And I can actually say make run because I'm fancy. It says, guess what? Hello World. What kind of file is this? Well, guess what? We can use the file command. We can say file, hello world, and it'll tell us that it's an executable. It's an ARM64. This is an M1 Mac. So if you compile this on a Raspberry Pi, it would also be an ARM64. You might have it as a x86 executable if you're running a normal Windows machine or a Linux machine. And it says that it's executable. And that means that we can execute it. And we can actually, this is a terrible idea, but we can do this. We can actually look at this file. Head will give us the first 5 lines of a file. My computer is going to go beep, 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 and it might ruin my terminal because it'll use some interesting commands. And that's what it looks like. Not super useful to us, but we can actually read some of it, which is interesting. We'll talk about, if you look through this, you'll get to know a little bit more about programs. But there is something special up here. There is something called a magic number. There's a few things to make a program executable in Linux or Unix, which is that it has to be executable. So you can see that I have the X bit set on my executable here. You can see the X is here, here, and here. So it looks like anyone can read it and execute it, but only I can write to it, which is great. I like that. And that will let people execute it. And that means that you can literally say /, which will say this current path, this file, run it. And it'll run it as a program. That's it. So this is a compiled program. It is machine code that is all packed in there. And with different compiler commands, you can actually see the machine code that is created as assembly. And that is something that is human readable, even though it's just masking binary for us. And that's it. It's an actual executable. This is a binary executable because it compiled from source code, which is human readable. We can literally cat hello world.c. And it made it into an executable, which we can't read. And that's fine. We don't have to. There's not a lot more to say about that other than the fact that when Clang, which is what my makefile used to compile that, or CLang, I know it's CLang. I call it Clang. I'm sorry. When that looked at our program, it looked at our program holistically. It knew about all of our libraries. It knew about all of our dependency libraries, our system libraries, local libraries, everything at once. And it linked it all together. And it could look at it as an entire unit. And that is not true for interpreted programs. Interpreted programs run differently. They are literally read from top to bottom as a script. And if you think about what the word script means, you might have a bunch of lines in an actual play and you read them one by one. That is what Python does. If we had a Python program, which I don't have one handy right here, I'm just going to pause it for a second. now that we have a Python program, which is inside of the languages demo. This is the unit test demo, just because there's lots of nice code here. If I looked at sumcode.py, you'll see that there's a bunch of functions. And what Python will do is it'll read in this first function and it'll say, okay, I know about the add function now. Actually, I skipped a line. First, it's going to say, I need to find and import random, which is a system library. Then it's going to read in add, it's going to read in multiply, it's going to read in crapfib, which is Fibonacci done in a terrible way. There's a bubble sort in here, because why wouldn't there be? An insertion sort, it actually does some cool stuff with profiling. And then it runs it all. This is a bit of a magic line of code that will check to see if this is being run as the main function. So it's actually Python was called on this, and it'll read in line by line down here, and it'll read in add, it'll read in multiply, and it'll execute these as it goes. It'll run and execute add, which it knows about because it read it in first. But there's a problem. If I would have defined add below here, Python would be coming along and say, I don't know about add because add is defined down here. You've seen that in any programming language if you've tried to use a variable before you've defined it or assigned it at minimum. And then it'll be like, what is X? I've never heard about X before. And that's the exact same thing that's going on, because this is an interpreted language. It interprets the source code at runtime. So there's no compilation step. It goes straight to running. So Python is a program that reads programs and executes whatever lines of code that's in there, which is actually kind of cool. Obvious perk, well, if you don't use a line of code, it'll never be executed and it'll never even be considered. The bad part is that that piece of code will always be in your code base. You'll have to use different tools to actually see if, oh, I never use this function. I never run this line of code. That is all to do with profiling and linting, which is actually what this is here for. And you can check that out. It's very nice. But it's also slow. Because it's reading it in line by line, it sees a library import and it says, okay, I need to import this library. And then it tries to import that library and might fail. And then it would fail in runtime to actually pick up that line of code. So there you go. If the library doesn't exist, you don't know about it beforehand. So let's say we have our main. That's going to go out and either run a function or read in something as a library. We're going to say that this is an import. Cool. And that's going to read in this library. I'm going to call it library 1. And this one's first line is import. So it's going to import library 2. Okay, cool. Library 2 actually depends on library 1. But library 1 is still being read in. It got to like line 5 in here and made the jump to the next library. It got to line 7 in here and it said, I need to get library 1. Well, it's not read in yet. I don't know anything about this and it has to fail, which, guess what, isn't ideal. And that is, oops, I apparently wrote something. What the demo is in, that's one back. I'm going to find my demo. One second. That is the demo that is inside of this languages folder. So I have a imports folder, and it says main.py, which isn't that interesting. It just imports something and then runs get number 60. Okay, well, module 1, get number 60. You can see that it's going to get to line 1, and it's going to import module 1. That's inside of my libraries folder. So what is inside of module 1? Well, from blah, this folder, import module 2. And then given module 2, do a little bit of math. And you can see that I do a little bit of math, not in a function. I actually do it live, which is what breaks this. One of the many things that this is horrible for. And then module 2, which it just imported, guess what? Imports module 1. Import module 1, and then I want to add 10 to it. Well, module 1.10 does, when we ran this, how far did we get? Can I split this? I can. So I'm going to open up module 1 here. It got to here, and 10 is defined down here. So module 1 was imported first. It read this line of code in, jumped to here, imported line 1, and then, well, I don't know about 10 from module 1 yet, because that is defined here. And because we're reading it in line by line by line, that doesn't work. And that's bad. And you can only find this out when you run this function, or when the imports actually run. And sometimes, depending on which one you import first, it'll work or not work, because it'll read in a way that works, and because everything was defined, or it'll read in a way that doesn't work because the things are defined in the wrong order and there's circular dependencies, which is what this is called. This is a circular dependency. And if I try to run main, Python 3, main.py, it will throw up a whole bunch of garbage that I don't really want to see. And I will see that it will say most likely to a circular import. Interestingly enough, this is Python 3.9, I believe. 3.8 gives you a different error message. So they've tried to make it a little nicer. Not super successful, but it's better. So compiled, just to wrap that idea up, compiled programs can see everything at once and compile them. If there is dynamically linked libraries, those happen at runtime. That's different, and that's a different ball of wax. But it should be able to see everything at once and compile into an actual executable. Interpreted languages are source code. And if you delivered it, you would deliver source code, which actually has some problems there too. And from there, it's going to read in line by line and execute. And that also means that you can't get any optimizations. Compilers these days are incredible at optimizing our code. Like, the code that we write is for humans and should be for humans. But your compiler is going to look at it and be like, well, I'm writing this for a machine. So it's going to take a for loop that runs 3 times, and it'll actually unroll it so there's no actual loops there because branches are slow and problematic. Okay, so it can then pipeline all of that and do lots of very cool things on the processor and optimize our code. And then in that executable, it'll be highly optimized. And there's optimizer flags built into Clang. I believe it's -O. Don't quote me on that. And you can either say, make this the smallest file possible, or it can be the fastest file possible. It doesn't really care about the file size as long as it's highly optimized. Neat. Different goals. Interpreted languages, it can't do that. It's reading it in line by line. There is no step it can take to say this is not optimal. There's no way it can optimize your code as it goes because it's too busy running your code. Whew. But there's another perk to interpreted languages, and that is that it's called a REPL. Read, execute, programming loop. I just typed Python, in case you didn't catch that. Python 3. I have like 3 different versions of Python on here, so I have to do that. And you can see I'm running Python 3.9.7, September 3rd, 21. Oh, okay. Nice update. Love it. Compiled with Clang. Very cool. And I can say x equal to 1, and x plus equals 1, and I can print out x. And this is a programming language. I can have a comment, I guess. You can inspect variables. You can make new variables. I could define a whole class in here, although it's very difficult to. Or let's do a function, add x, y, colon, space, return x plus y, enter. Then I can say add 34 and 6. And it'll do it for me. And whatever returns will get displayed to you as the output of this loop. So you can see the programming loop. I'm writing a programming language live, and it's interpreting it live. Python is an interpreter. I'm just feeding it data very slowly compared to what it can do. This is not, would you believe that I'm slower than cat, which will just throw code at, or whatever text file at something. Yeah, well, my little fingies can't type that quickly. But what is this useful for? Well, what if I was struggling on a line of code? Well, I can press up, and I can repeat lines of code, and then I can make it go faster. Okay, how do I get this one line of code? What are my arguments. Do I want to pass this or this? And I can play with it live, and I can see that feedback live. Instead of hitting play and then like, oh, well, it takes a minute to get back to my line of code. You should have written a unit test, whatever. And then come back, see it, stop, fix it, run again. You don't have that stop, fix, run again. It's just go, try, which is quite beautiful. It's a wonderful way to write a programming, just a hack on your one line of code. And that's really easy. Only interpreted languages can do this. You can hack some compile languages to kind of do this. Dr. Java on Windows could do a bit of a Windows REPL, but it's not built into Java. Python, you get it for free because it's just the way it works. Guess what? Bash is a programming language. I'm not super good at it. I'm not gonna lie to you. But this is a REPL. You've used a REPL. It's not a new concept. So isn't that beautiful? And it's just a different way to think about a programming language as line by line read in versus compile this whole corpus of things and then send it all at once. Oh, I'm sorry. I'm very excited about that. Let's jump over to, that didn't work. That's okay. Cam and desktop. A notebook. This is not new anymore. But it is something that is picking up steam, especially for scientists like yourself, where I just typed in Jupyter Notebook, and this is not the file I want to be in. So I'm going to hit Control C here because I want it to be in my other example notebook. I want it in Notebook. Wherever you run this command, that's going to be your root folder, and then it pops up here. I could traverse here if I wanted to. You couldn't run this at the base of your user folder, and then you'd have your whole user folder. You'd have to get through it all. I prefer this. It's nice. You can see that the extensions are I, Pi, and B. That is for Iron Python, where that's kind of the roots of this. And I'm going to show you a demo. This is not unlike the GIF that I showed in the actual lecture slides here. I have a GIF down here somewhere. I actually lost that notebook, so I kind of recreated it. But the idea is that you have documentation, like the idea, like what idea am I working on here? What is the notes I'm making to myself, future version of myself? I'm trying this here. And you can do it in Markdown, including having images. And if you're a mathlete, you can do LaTeX right in here. I didn't have to add anything else, and it will just go. And there's my image. You can actually read it. You can see my LaTeX rendered very nicely. I could do a big, beautiful thing there if I wanted to. And then I wanted to do a math. And what I'm going to do is I'm actually going to clear all my outputs. Current outputs clear. And then I'm actually going to run all of mine. I believe that's this button. Restart the kernel. Quick aside about a kernel. There is Python running behind here. And it's like I just typed Python into the command line, and it's a live REPL. That means it's carrying state all the time. So I can clear my entire state and start again. And that is the kernel of Python that they're talking about. Now I'll restart. That's fine. Blue. Not trusted. Sorry, that's funny. And you can see that my for loop here, I just squared everything because why not? Printed out, and it prints out to the below. So I have my documentation in Markdown. I have my code trying something. I have my output. And I can save this, and this will actually get rendered on GitHub, which is beautiful. You can go check this one. I'll leave the outputs in there for you. You can't run it on GitHub, but you can see it on GitHub. But there's something interesting. There's some state issues. So I just ran this one. You can see I ran it 5th. I want to run this one. It's always going to move me to the next cell because I don't use this enough to not use it. And you can see that every time it's incrementing I. Is that what you want? Possibly not. You have to be worried about resetting your state. It's like, oh, the problem is I've been hacking around. Okay, that's fine. I'm going to go back up here. I'm going to run it. And if I didn't have x equals 0 here to like reset my state, all of a sudden I'd have my previous variable still floating around in my current run. And then it turns into a hot mess, which is interesting. But it is sometimes useful, but you just have to know about it. But the cool thing is, this is just Python. I could import libraries. If I had a library folder right next door in this folder, I could import my own libraries, and that's nice. Or I can import system libraries. I imported URLlib and JSON using a API. So I'm fetching my own URL with URLlib. I'm parsing it with JSON, and then I'm using a nice print statements to print it out nicely, and it says, this is your IP address, and that is currently my IP address. Come hack me. Please don't. And then I also just said as dict. And you can see here, whatever my last line of code is, gets printed to the output. So you can see that if I run this again, it'll work again. You can see the JSON that was returned to me from this API, but I can also see my nice pretty output that I wanted to try to print. And all this is a REPL. It's running blocks of code. So you're passing this as one big chunk of like execute all this stuff. But other than that, it is just a REPL. So it's just building on the shoulders of giants. We have this cool thing, and let's make it even cooler. This is very nice. I'm going to clear and run all, restart and run all, which is super useful, by the way, to just clear it. And I will commit this as is, because why not? And I'll commit this to the GitHub repository, view it on GitHub, and you'll see that it actually works, which is very cool. So I think that's pretty much covers everything I want to talk about. Compiled languages are faster. They always will be. Go, Rust, C, C++, they'll always be faster because you can have those optimizations. Interpreted languages are nice because you get all these other fun bonuses like REPL, and it can do some lazy loading of libraries and really neat things because it doesn't have to see everything at once. So there is perks to both. Oh, strongly and loosely typing, is that in here? Should be. See, Python, I didn't actually show you this, is loosely typed. I'm going to do that right here. I'm going to name a variable v, words, and now v is equal to 0, and v is, hold on, I'm going to have a little bit of fun here, messing around. V equals words, v is equal to 1. JavaScript gets pooped on but for this all the time. V plus 1. Ooh, Python's going to be grouchy about that. So I run this, it'll work. It switched from a variable of type string to a variable of int, added 2 to it, and then printed out 2. But I could run this, and then this, and now it's like, can only concatenate str, not int, but I see that v is an int. Do not reuse variables in a loosely typed language. This will happen to you because v, and I can actually prove this to us by using the type command, is a string. And we know that because there's like 3 lines of code. It's kind of obvious. But you might run into problems if you're not being careful. I'll leave this here too because it's kind of fun. Strongly typed languages are nice because you don't run into these problems. If you're trying to mix types, it'll get grouchy with you right away because it's looking at everything as an entire corpus. Interpreted languages, this is very natural for it because it can change types because everything's getting read in on the fly. Sure, why not? Why wouldn't we do that? It's a bit dangerous. Compiled languages can use optimizations because it knows that an int will always be 32 bits. So I'm going to have that register here, and then I'll always be able to reference it and blah, blah, blah. And it can do all of those optimizations again, where this can't. Everything is dynamic, but it's also quite beautiful. So, classic question, which language is best language? Depends on the problem you're trying to solve. Loosely typed languages are very dangerous in groups of programmers because it's hard to know what types are floating around. And if you're writing a library for someone else, what arguments are you looking for? What are the types of these arguments? Compiled languages, on the other hand, you kind of program more slowly because you have to say declare your variables as an int, and then you use it, and then in the case of C, you have to release your anything that you mallocked and all of these things that are very nitpicky, but it's going to go much faster. So in my opinion, interpreted languages that are loosely typed are fast to program, but slow to execute. On the other hand, compiled languages are slow to write, but fast to execute. So the question is, how often are you executing this? If you're only executing it once, write it quickly, and if it takes a little bit longer on that one run, it doesn't really matter. If you're executing it many, many times, well, those start to stack up. Maybe you want to use a compiled language. Are you working with a team? Maybe use a compiled language, or at least a strongly typed one. I hope you had a good time. I hope you learned something. I'll talk to you next time.